According to the National Electrical Code, each circuit in a conduit generally requires a dedicated ground conductor. In the case of the 3/4-inch PVC conduit containing two 3/0 multiwire circuits, each operating at 208 volts and drawing 20 amps, with each circuit using number 12 wire and carrying a load of 9 amps, and supplying 6 120 volts lighting circuits, creating two sets of 3 hots, 1 neutral, and 1 ground for a total of 10 wires, you would need to pull 2 number 12 ground conductors. This is because each multi-wire circuit needs its own dedicated ground path. Now let's consider electrical metallic tubing, or EMT conduit. EMT can be used as a ground conductor, but this is contingent on specific conditions being met. Firstly, the EMT must be securely connected to a ground rod or another recognized grounding electrode. Secondly, all connections within the EMT system must be made using approved methods. Examples of approved methods include set screw connectors specifically listed for grounding, or the use of bonding jumpers to ensure electrical continuity. If both of these conditions are satisfied, it may be permissible to run only one number 12 ground conductor through the EMT conduit to serve both circuits. However, it is crucial to understand that relying on the EMT as the primary ground path necessitates meticulous installation and maintenance to ensure the integrity of the grounding connection over time. To ensure compliance with the NEC and to provide a safe and reliable electrical system, it is generally recommended to pull a number 12 ground conductor for each set of circuits, regardless of whether the conduit is PVC or EMT. This provides a dedicated ground path for each circuit, which minimizes the risk of electrical shock or fire. This approach offers a redundant level of safety and can simplify troubleshooting in the event of a fault. It's important to remember that local electrical codes may have additional requirements or may interpret the NEC differently. Always consult with a qualified electrician or electrical inspector to ensure that your wiring methods comply with all applicable regulations. Furthermore, consider the specific installation environment and the potential for corrosion or mechanical damage when selecting the appropriate grounding method. In corrosive environments, for example, additional measures may be necessary to protect the EMT and maintain its grounding effectiveness. When working with electrical systems, always prioritize safety. To energize circuits before working on them, use appropriate personal protective equipment, and follow all applicable safety procedures. If you are unsure about any aspect of the wiring or grounding, seek assistance from a qualified professional. To summarize the key points, firstly, for PVC conduit, always run a dedicated ground conductor for each circuit. Secondly, for EMT conduit, while it can be used as a ground path under specific conditions, it's generally best practice to run a dedicated ground wire. Thirdly, always consult with local codes and a qualified electrician to ensure compliance and safety. Remember that proper grounding is critical for protecting people and property from electrical hazards. Now let's delve deeper into some of the considerations that go into selecting the appropriate grounding conductor size. The NEC specifies minimum grounding conductor size is based on the size of the overcurrent protection device protecting the circuit. This is because the grounding conductor must be able to safely carry the fault current back to the source in the event of a short circuit. Refer to NEC Table 250.122 to determine the minimum size of the grounding conductor based on the size of the circuit's overcurrent protection device. In the example given, the circuits are protected by 20 amp breakers. According to NEC Table 250.122, a 20 amp overcurrent device requires a minimum number 12 AWG copper grounding conductor. Keep in mind that this is the minimum size, and you may choose to use a larger grounding conductor if desired. A larger grounding conductor will provide a lower impedance ground path, which can further improve safety and reduce the risk of voltage drop during a fault. In addition to the size of the grounding conductor, it's also important to consider the type of grounding conductor. The NEC recognizes both copper and aluminum grounding conductors. Copper is the most commonly used material due to its excellent conductivity and corrosion resistance. Aluminum grounding conductors are permitted, but they must be sized larger than copper conductors to provide equivalent conductivity. When using aluminum grounding conductors, be sure to use connectors that are specifically listed and labeled for use with aluminum. Another important aspect of grounding is the bonding of metallic enclosures and equipment. Bonding is the process of connecting all metallic parts of an electrical system together to create a low impedance ground path. This helps to ensure that all metallic parts are at the same potential, which minimizes the risk of electrical shock. The NEC requires bonding of all metallic enclosures, raceways, and equipment that are likely to become energized. This includes items such as panel boards, junction boxes, motor frames, and appliance housings. Bonding is typically accomplished by using bonding jumpers or bonding screws to connect the metallic parts together. When installing bonding jumpers, be sure to use the correct size and type of conductor and ensure that all connections are tight and secure. It is also important to protect bonding jumpers from corrosion. Now let's talk about some common grounding mistakes to avoid. One common mistake is to use the neutral conductor as the grounding conductor. This is a dangerous practice that can create a shock hazard. The neutral conductor is intended to carry the normal unbalanced current in a circuit, while the grounding conductor is intended to carry fault current. If the neutral conductor is used as the grounding conductor, fault current can flow through the neutral conductor, which can cause it to become energized. Another common mistake is to omit the grounding conductor altogether. This is a violation of the NEC and can create a serious safety hazard. Without a grounding conductor, there is no path for fault current to flow back to the source, which can result in a voltage buildup on metallic parts of the electrical system. This voltage buildup can create a shock hazard if someone comes into contact with energized metallic parts. Another mistake is to use undersized grounding conductors. As mentioned earlier, the NEC specifies minimum grounding conductor sizes based on the size of the overcurrent protection device. Using undersized grounding conductors can prevent them from safely carrying fault current, which can result in overheating and fire. Always refer to NEC Table 250.122 to determine the correct size of the grounding conductor. Finally, it is important to properly terminate grounding conductors. Grounding conductors must be securely connected to a grounding electrode system, such as a ground rod or a metal water pipe. The connections must be made using approved connectors and methods. Loose or corroded connections can prevent the grounding conductor from effectively carrying fault current. In summary, proper grounding is essential for electrical safety. Always follow the NEC and local electrical codes when installing and maintaining electrical systems. Use the correct size and type of grounding conductors, bond all metallic enclosures and equipment, and avoid common grounding mistakes. If you are unsure about any aspect of grounding, seek assistance from a qualified electrician or electrical inspector. The integrity of the grounding system is paramount in ensuring the safety and reliability of electrical installations. Now, let's consider some practical examples of grounding in different scenarios. Firstly, imagine a residential dwelling with a subpanel located in a detached garage. The subpanel is fed from the main service panel in the house. In this case, it is crucial to install a 4-wire feeder to the subpanel consisting of 2 hot conductors, a neutral conductor, and a separate grounding conductor. The grounding conductor must be connected to a grounding electrode system at the detached garage, such as a ground rod or a concrete encased electrode, also known as a U for ground. The neutral conductor and the grounding conductor must be kept separate in the subpanel. This prevents neutral current from flowing through the grounding conductor, which could create a shock hazard. Secondly, consider a commercial building with multiple branch circuits feeding various loads. Each branch circuit must have its own dedicated grounding conductor, sized according to NEC Table 250.122. The grounding conductors must be connected to a common grounding busbar in the panel board. The grounding busbar must be connected to the building's grounding electrode system. All metallic enclosures, raceways, and equipment must be bonded together to create a low impedance ground path. Thirdly, think about an industrial facility with large motors and other heavy equipment. In these applications, it is particularly important to ensure that the grounding system is robust and reliable. Grounding conductors must be sized to handle the large fault currents that can occur in these systems. It may be necessary to use multiple grounding electrodes to provide a low impedance ground path. Regular inspections and maintenance of the grounding system are essential to ensure its continued effectiveness. Let's discuss some advanced grounding techniques that are used in specialized applications. Firstly, isolated grounding is a technique used to reduce electrical noise in sensitive electronic equipment. In an isolated grounding system, the grounding conductor for a particular circuit is isolated from the building's main grounding system. This prevents noise currents from circulating through the grounding conductor and interfering with the operation of the sensitive equipment. Isolated grounding systems must be installed in accordance with the NEC. Secondly, equipment grounding conductors with impedance are sometimes used to limit the amount of fault current that can flow in a grounding system. These conductors have a built-in impedance that reduces the magnitude of the fault current. This can help to protect equipment from damage during a fault. Thirdly, sensitive electronic equipment may require surge protection to protect it from voltage transients caused by lightning or other electrical disturbances. Surge protection devices, or SPDs, are installed in the electrical system to divert surge current away from the sensitive equipment. SPD must be properly grounded to be effective. Remember that grounding is not a one-size-fits-all solution. The specific grounding requirements for a particular installation will depend on a variety of factors, including the type of equipment being used, the voltage and current levels, and the environmental conditions. Always consult with a qualified electrician or electrical engineer to determine the appropriate grounding methods for your application. In addition to the technical aspects of grounding, it is also important to consider the legal and regulatory requirements. The NEC is the most widely adopted electrical code in the United States, but many states and local jurisdictions have their own electrical codes that may be more stringent than the NEC. It is essential to comply with all applicable codes and regulations when installing and maintaining electrical systems. Failure to comply with these requirements can result in fines, penalties, and even criminal charges. Furthermore, it is important to be aware of the potential liability associated with electrical work. If someone is injured or property is damaged as a result of improper grounding, the responsible parties may be held liable for damages. This is why it is so important to hire qualified and experienced electricians and to ensure that all electrical work is performed in accordance with applicable codes and regulations. In conclusion, grounding is a complex and critical aspect of electrical safety. By understanding the principles of grounding, following the NEC and local electrical codes, and working with qualified professionals, you can help to ensure the safety and reliability of electrical systems. Remember to prioritize safety, be diligent in your work, and never hesitate to ask for help when needed. Electricity is a powerful force, and it must be treated with respect. By taking the necessary precautions, you can protect yourself, your family, and your property from electrical hazards. Firstly, always disconnect power before working on any electrical circuit. Secondly, use the correct tools and equipment for the job. Thirdly, follow all applicable codes and regulations. Fourthly, inspect your work carefully before energizing the circuit. Fifthly, test the circuit to ensure that it is working properly. And sixthly, if you are ever unsure about anything, ask for help from a qualified electrician. By following these simple guidelines, you can help to ensure a safe and successful electrical installation.